Hi everyone. Today we're going to be talking about uncertainty in a linear regression. And so I've set up this kind of toy experiment here where we have some sort of wind speed sensor here that we're putting in our wind tunnel, and we're going to program our wind tunnel to pull through air at various velocities. And so the wind tunnel has an independent sensor on it that we trust, and we can set the velocity to anywhere from 1 to 20 miles per hour in 1 mile per hour increments. And then our sensor is going to put off some voltage, and we're going to compare that wind speed that we know from the wind tunnel sensor to the voltage that's coming off of our, in this case, cup and vane anemometer. And so we would sort of set that up as a table here. And we would put in our wind speed and put in our voltage. And we learned in the last video that we are going to fit some line where we can get the y points in the fit using the wind speeds that we measured by calculating some slope and some y-intercept, m-fit and b-fit in this case. And so we found that the slope is equal to the sum of these individual, the multiplication of these individual terms here. So we're taking each wind speed and subtracting the mean, and then we're multiplying that by each voltage where we've subtracted off the mean. And then we're going to divide that by this summation down here where we're taking every wind speed, subtracting the mean, and squaring it, and then summing it all up. And so I've linked to a Excel spreadsheet here where we've plugged in some voltages for given wind speeds. And I will upload this wind speed calibration spreadsheet so you can take a look at each of the individual formulas. But here we're calculating x bar, the average wind speed, and we're calculating the average voltage. And then we calculate each term in these three summations, so each of the individual terms inside of these parentheses. So here's xi minus x bar, and here's yi minus y bar. So we notice, so we need a series for this one, which is the same as this one down here, and then we need a series for this one. So that's each of those terms run along here. And then here's the individual terms in the multiplication in our numerator, xi bar times yi minus y bar. And then we calculate each of those terms, and then the sum is over here. And then here's our denominator, each of those terms, and the sum here. And then we can calculate m-fit as that summation in that first row divided by the summation in that second row. So it'll be 68.518 divided by 665. And so we calculate m-fit. And then b-fit is calculated as y bar minus the m-fit that we just calculated multiplied by x bar. And so we have all those here in our spreadsheet, so we can do that quick calculation and get b-fit. And so then we can plot our calibration data. So this is our wind speed versus voltage. And you can see we have a generally linear trend. It looks a bit noisier out here at high voltages. That's common for some sensors. Some sensors are noisier at the lower end. It all depends on how they generate their signal. But then we can plot m-fit, our line that's described by m-fit and b-fit. And so we get this red line here. So this is our best estimate of the linear fit. It may not be representative of the actual linear relationship in the sensor. And so we have some uncertainty here because we didn't get 100 points at each wind speed, and we didn't calibrate at wind speeds from 1 mile per hour to 20 miles per hour in increments of 0.1, right? And so we know that if we only took these 20 points here, there's going to be some uncertainty in that fit. So the question becomes, how can we calculate a confidence band where the true line is likely to lie? So in general, the method that we use is described here, and I'm not going to derive it because we'll probably do that in some subsequent class during your time here. But we're just going to say for now that y band is equal to some y fit slope that we just calculated, or some y fit line that we just calculated, shown here in red, plus or minus some statistical quantity here, multiplied by some standard deviation of our fit. And we'll notice this looks just like our confidence interval for a single input measurement, at least for the mean value, right? We had the mean plus or minus some statistical quantity multiplied by our standard deviation of our sample. And so we're doing that exactly here, but in this case we're using this t-distribution. And we usually get t-distribution from a lookup table, or you can use an online calculator. And we'll put in these values here, nu and alpha. So for a single input measurement system, we only had to put in our confidence interval, because for a Gaussian distribution, the number of samples that we took is not, or the shape of the distribution is not dependent upon the number of samples that we took or the number of degrees of freedom, so to speak. And so the t-distribution will actually change shape relative to the number of samples that we took. And so we, in addition to the alpha, the confidence level that we're interested in, we also need this quantity here, nu, which in our case is n, which is 20, the number of calibration points we took, minus 2. And so we get this standard deviation from the fit after we've looked up our t value. We get this standard deviation in our fit from this calculation here. So again, we see that it has our number of samples, which we know how to calculate. Then it has the difference between each data point and the mean, right? We know that that's how we calculate variance and subsequently standard deviation for a single input measurement. And so we see that here. We have our yi minus our y bar and our xi minus our x bar. And here we're doing a summation, and here we're doing a summation, but here we're not. We're not summing over the individual points. So S sub y fit is going to be a series of data values. This will have a value for every xi value. So the width of our band will actually change depending upon where we are in our calibration range, and we'll show that in a second. But we notice that xi minus x bar is squared here, and then we're taking a square root. And so we would expect that, maybe there's some nonlinear shape, but in general, we would expect that when xi is far away from our mean value, it should be wider, our confidence band should be wider than when it is close to the mean. That makes sense because out farther away from the mean, we don't have as many neighboring points to reference off of. So we would expect that our confidence intervals are a little wider out there. So what does that actually look like? So here we show that. Here's our fit with our calibration points in black, and then these lighter red dashed lines represent this 95% confidence interval on the fit, right? So this is not the 95% confidence interval where we would expect a new point to lie if we were to say calibrate at 15.5 miles per hour. We wouldn't expect the 95% confidence interval for that point to necessarily be in these dotted lines. We would expect it to be potentially farther out. But if we added that new point and then calibrated a new fit, we would be pretty confident that that fit would lie within these dashed line bounds. So as I stated before, the further we get from x bar, which in this case is 10.5, the wider our bands get. So we can see that slightly wider out here and slightly wider out here, slightly more narrow here. Now, if there's more noise in your data, that change in width will become more pronounced. So we could sort of stop there and say, all right, that's how we calculate some bands. But I wanted to explore this idea a little further. So it turns out that I actually got these calibration points by adding some noise to a line that I already knew. Now, in practice, you won't know this, but I'm doing this to prove a point. So I said, if our calibration points, our yi's, are equal to the actual slope plus some little noise level at each calibration point in the slope times xi plus b, which is the actual y-intercept, plus some little noise for each point in that intercept. So I've added a little bit of noise for each point into the slope and a little bit of noise into each point for for the intercept. And those are beta and alpha at each point, respectively. So what was that true line that I put in this case? So the true line that I actually put in is shown below in blue. And it lies just within our 95% confidence interval. And we see that it's very close to the red line near the center of our calibration region and gets a little farther and farther away as we move out. Why? Because we didn't match the slope exactly. And so that slope, the farther and farther we get from the mean, is the mismatch is going to be farther and farther away. So I wanted to know, well, what if we just did this calibration again? So then we just simulate, okay, well, I went in on Monday and I took 20 calibration points. But what if I went in on a Tuesday and took 20 new calibration points? Well, that noise would still be there, and so those 20 points would be slightly different than the 20 points that I took yesterday. And then I go in the next day and the next day and the next day. And what if I went in for, say, 500 days straight and I took 500 sets of calibration data? And then I fitted one of these red lines to each set of that calibration data. Where would my 500 lines actually lie? Well, I would expect that 95% of them would lie within something that looks like this, an uncertainty band of this width. Now, maybe it wouldn't be an uncertainty band that's centered on this red line. It should be an uncertainty band that's sort of centered on this blue line. And so if we plot all 500 of those calibration sets and their fits, and then we plot the average calibration uncertainty in each one of those fits, and then we center it around the actual blue line, how closely do they match up? And so that's what we see here. Now, here's my 500 red lines. You can see when I plot all of them together, they sort of make this band, which is cool. And that band is roughly in line with the confidence intervals that we would expect from 20 or so calibration points if we center that band on our actual blue line fit. Now, this is slightly different than what we'd expect because I added some noise to the slope and I added some noise to the y-intercept separately. And so what that means is that the larger the value of wind speed, the larger the noise value once it gets multiplied into the slope. And so you can see that the effect of that is here. Down where we're at a wind speed of 1, we have a relatively small noise band. Right? Our points are generally concentrated in a really small amount of voltage. And that's because we're adding that little bit of noise in the B term from our alpha. But our beta is pretty small because we're only multiplying by 1. Out here, we're multiplying our beta term by 20. And so that noise band gets much higher. And so if we were just adding that noise via the slope, we would see that this noise this distribution of the black points would be relatively similar width all the way through. So that's why the envelope of red points, red lines, is a little wider out here than it is out here. But in general, we still see that shape agrees with our confidence bands, right? It's a little wider here, gets a little narrower towards the middle, and then a little wider out here. And so what did we learn? Well, our uncertainty bands are very important. We can see that any given calibration experiment can give us a curve that lies somewhere within our uncertainty bands, right? If we could have gotten any one of these red lines when we did that one calibration. And so how much can we trust it? Well, we can only really trust it within our uncertainty bands. And so be careful how much you trust your calibration fit. If you don't have an idea of your uncertainty bands, if you don't go through this effort to calculate it, you might as well not even do a calibration at all. And now one important note is that this assumed no nonlinear effects. In practice, we often fit slightly nonlinear signal responses to a linear regression. Now, why? Well, because it's convenient, number one. And number two is because it usually works pretty well. And furthermore, if we don't have an idea of how that sensor responds to given inputs, like if we don't have a better reason to fit anything other than a line, either the data has to look very clearly nonlinear, in which case we might choose an exponential fit, like a power law fit, or even a quadratic fit. But unless you have a really good reason why the data looks nonlinear, it's usually best to use a linear calibration. So that's it for uncertainty calibration. Soon in future videos, we're going to talk about digitizing an analog signal and what the size of our bin, how the size of our bins can influence some of these statistical quantities that we've been talking about in these previous videos. So see you on the next one.